So we talked about matrix multiplication, right? And now think about the following. Suppose I got a vector pi here and make a transpose. So it is a row vector and multiplied on the right by some matrix A. Suppose after being multiplied by this matrix A, what you get is actually some constant, let's say half, times the same row vector, pi transpose. Then, in that case, we say this vector, pi transpose, is an eigen vector, means that it maps back to itself corresponding to this matrix A. Okay. It might be a scaled version of itself. Every entry in the vector is scaled by some number. And this scaling factor is called the corresponding eigenvalue. In today's lecture, we'll be constructing 3 different matrices. Start from the simplest one based on our current intuition, and then point out why that doesn't suffice. And then suggest an enhancement. That's why we're going to go through a sequence of 3 matrices. And the final product is a matrix, what we call the Google matrix G, that captures the connectivity pattern of these web pages on the web. And we'll see that this matrix G is the so-called non-negative matrix, meaning that each entry in G sub ij, the ith row and jth column entry of this matrix G, for all the i's and all the j's, meaning every entry in this matrix G must be a non-negative number. It could be 0, but can be negative. And it turns out that there's a whole branch of mathematics in linear algebra that studies non-negative matrices with many properties. Okay, that's often called Perron-Frobenius theory of non-negative matrices. One of these results says that there will be a largest eigenvalue which is exactly 1. In other words, we can find an eigenvector associated with this eigenvalue for a given matrix, say A, such that pi transpose multiplied on the right by A returns nothing but the same vector pi transpose. Well, you can also write down this 1 in front of it. It's okay. That is the eigenvalue. Okay. Now you may say, why are we even going through all these matrix multiplication and eigenvector and eigenvalues for non-negative matrices? What has this got to do with Google's web page ranking? As we will see in the next 30 minutes or so, that the ranking is determined by the importance score vector pi, and pi really is nothing but the eigenvector associated with eigenvalue of 1 of a matrix, this Google matrix. Okay, instead of writing a generic matrix A, let's write down the Google matrix G. In other words, we will go through a sequence of steps to properly define matrix G such that the ranking importance score pi vector can be computed as the dominant eigenvector, the eigenvector associated with the largest eigenvalue, which happens to be 1, of this matrix G. And from this pi, we can then compute, we can then order the web pages to be displayed. So that's the game plan for the rest of the lecture.